So today's lecture would be an introduction to you know the basic simulation process. That is, I'll introduce briefly what Navier-Stokes equation is, what turbulence is, and then I'll talk about the direct numerical simulations. And if we have time left at the end of it, we'll talk about large eddy simulations as well, only briefly. I won't get into details of it. Uh, we'll not be talking about much about the models that are used, like RANS models and other models that are used in mean flow equations. Okay, so to begin with, we all know that for incompressible fluids, the governing equation is called the Navier-Stokes equation, and it is the Newton's law analog for fluid dynamics, or for you know uh, for media that is continuous. So this equation here, let me point it. So this equation here is the Navier-Stokes equation, and the term on the left hand side is your mass times acceleration. Except here, it's mass per unit. It's the mass times acceleration per unit volume, and on the right hand side you have your forces per unit volume. Okay, so it takes this form. Okay, hope you all know how the equations are derived, because I won't be getting into that. Okay, so this term dv by dt here is the material derivative. If it tells you, it quantifies the acceleration of a fluid. So if you in a continuous media, if you want to measure the acceleration of a fluid particle at that point, at a particular point, it will be given by this term dv by dt, and this would have an expression of expression similar to this. So your dv by dt, it will include the time derivative, that is your acceleration because of velocity changes with time, and it will have your convective derivative, so v dot del v. So this term is the acceleration that a fluid particle would experience as it moves through the medium. Okay, uh, on the right hand side there are three terms here. The grad p is the pressure, is the pressure forces per unit volume experienced by a fluid element. The term with mu, that is the viscous term. This quantifies the viscous forces, and the third term is the body force. Okay, uh, body force or any other kind of forcing that might be there. Now, as long as the forces, these body forces or the forcing are conservative, we can express them as a gradient of some scalar field, scalar potential function, and then include them in the pressure term itself. So for the most part of the lecture that we'll continue from here, will the right hand side would include the pressure term and the viscous term. Okay, only when we start talking about the numerical approaches, we'll have an additional f term which will include those non-conservative forces or any other kind of forcing that might be there in the fluid. Okay. Okay, so that was a brief recap to what Navier-Stokes equation is. It's the basic dynamic equation for fluid dynamic flows. Now to remind you of what turbulence is. So in 1883, Reynolds did an experiment in which he had a tank. This tank was filled with some fluid, and there was an outlet to this tank, to which he injected some dye. Okay, and he observed how the dye behaved with a non-dimensionalized parameter called Reynolds number. Okay, so this is, as you know, it is rho u d by mu, where rho is the fluid density, u would be the average velocity in this duct or pipe, d is the diameter of the pipe, and mu is the viscosity of the fluid, of this fluid in this pipe. So what he observed is, for low Reynolds numbers, the dye that was injected flowed in a laminar fashion, laminar, that is layer like fashion. It did not mix at all, except that except there might have been some distortion because of the diffusion, but it still maintained that identity. It was flowing in a layer like fashion. Whereas the Reynolds number increased, there was violent random fluctuations, and the dye that was injected immediately got mixed in the pipe. So that's what characterizes a turbulent flow. There are random, intense, violent fluctuations there, and it enhances the mixing and transport properties of the fluid flow. Okay. Now, turbulent flows are important because uh, they are often observed in natural flows. Uh, okay, and also why a flow becomes turbulent is because there are always disturbances present in a flow, present in the environment. Now, the laminar flow is one particular solution to your Navier-Stokes equation. Okay, this solution is always being perturbed. So if you remember your stability diagrams like this, so Navier-Stokes is one stable solution, and it is always being perturbed by the disturbances that are there in the environment. Okay, but for at low Reynolds numbers, the recovering force, that is the viscous damping that is there, is high enough to bring it back to the stable solution. However, as the Reynolds number is increased, so if you look at the Reynolds number expression, an increase in Reynolds number can be viewed as a reduced viscosity of the flow. So essentially, what happens is the recovering force becomes weak, and your flow it transitions from this stable state to another stable state, which is the turbulent flow. Now, this turbulent flow is characterized by random intense fluctuations and enhanced mixing rate. Now, this enhanced mixing rate is of importance to engineers because of course your mixing is enhanced, and this will have applications um, in, like, say, IC engines, where you want your fuel and air to mix as quickly as possible, and your transport properties are enhanced as well, which means your momentum transport is increased. So this will increase the drag forces. So you need to understand how these transport properties are enhanced by the turbulence itself. And once you have an understanding of how these transport properties are enhanced, you can manipulate the flow to either increase the mixing properties when you want it, or decrease the mixing or transport properties when that is what is desired. Okay, so in our efforts towards understanding the turbulent flows, uh, we do something called Reynolds decomposition. So obviously our velocities. So if in a turbulent flow, if you put a probe in the flow itself. So let's say this is a turbulent flow. These are the random fluctuations that are there in the flow. Now, if you put a probe here in this flow itself, uh, your velocity is measured by this probe. It will fluctuate randomly in time. So if you plot it with respect to time, it will fluctuate randomly. Also, in this flow itself, if you fix the time at so if you fix the time, and you take a snapshot of this flow, like in a PIV, and if you observe the velocity field, then also it will be randomly fluctuating. So there are fluctuations both in space and time in a turbulent flow. So what Reynolds decomposition does is it decomposes the velocity signal into a mean and fluctuating part. Now, this decomposition can be in time, which is the temporal decomposition, where you use the time average and the fluctuating part, or it can be in space as well, where again you decompose it in terms of space average and the fluctuating part. So for the temporal averaging, your mean velocities would be a function of space, and for your spatial averaging, your mean velocities would be a function of time. I hope I'm audible, right?
Yes.
Okay.
Yeah, yeah.
Okay. So this is how we time average. So we time average over a window from 0 to t, and the thing is, this window should be large enough to to not be affected by these fluctuations, and it shouldn't be so large that if there are any large scale unsteadiness in the flow, that those unsteadiness be damped out as well. For example, if you have um, let's say if you have a flow in a pipe, which reverses in time, so the mean velocity is periodic in time. Okay, it goes positive and goes negative, and then there is this cyclic nature to this flow. An example of this would be in your blood vessels, where the blood goes forward and then backward rhythmically. Now there might be this flow might be turbulent. So when you average, so there might be turbulence in the flow like this. So when you average, your time scales should be large enough that these fluctuations are averaged out, but it should not be so large that these large scale unsteadiness is also averaged out and it becomes zero. So you should have that large scale part as well. But for most of the cases that are relevant to the research purposes, we look at flows which are stationary in time, so there is no large scale unsteadiness. But if there is, you have to take care of that. So in a similar fashion, we can also define spatial average velocities like this. And once you have the average, you get the fluctuating part by subtracting it from the instantaneous part. Okay. So now we'll look at the effects of this decomposition on the equations of motion itself. So this here is the continuity equation, and the notations I'm using here are tensor notations. Uh, are any of you unfamiliar with what a tensor notation is? Well, I'll tell you anyways. So, so for the continuity, I've used here del ui by del xi. Okay. So in the tensor notation, we look at the indices. If there are repeated indices, it means that there is a summation over that index. Okay, so this essentially is del u1 by del x1, del u2 by del x2, and del u3 by del x3. Okay, so for an incompressible flow, this part is equal to 0. So in tensor notations, your continuity equation is del ui by del xi equal to 0. Now, if had this expression been del ui by del xj, this since the indices are not being repeated here, this is there is no summation here. Uh, but your indices can go from 1, 2, and 3. Both I and j can go from 1, 2, and 3. So this notation actually represents all your gradients. So it can represent del u1 by del x1, del u2 by del x2, del u3 by del x3. Similarly for v, del u2. Okay, so it can represent all the 9 components. We can represent all the 9 components using this simple expression. So this tensor notations are used for uh, like this. So an average of the continuity equation would be I'll use an overbar to represent the averaging process. Now the averaging operator and the differential operator will be commutative, so it will become del by del xi of ui average. Okay, so as per our decomposition, the average of the instantaneous flow velocities would be ui. Again, I'm using capitals to represent the average. So the large U symbols are the average velocities. Okay, so when you take the average of this thing, the equation becomes the del by del xi of capital ui is also equal to 0. So the mean velocity satisfies the continuity equation. Okay, now if you subtract this from the instantaneous one, you'll see that the fluctuating velocities also satisfy the continuity equations independently. Okay, now so this is the momentum equation. If you remember the Navier-Stokes equation, I had shown that your dv by dt operator includes a time derivative and the convective derivative v dot del of v. Okay, so this term is the time derivative here. V dot del is the uj del by del xj operator, and it operates on the velocity components ui. Okay, so this is the momentum equation written in tensor notations. Okay, your grad p would be del by del xi of p, and the viscous term is written as follows: del 2 by del xj2 of ui. Now, if you take an average of the entire equation, you'll get the equation for the mean flow for the mean velocities. So the averaging operation is commutative, so the average will get inside the derivative operator, and you'll get the time derivative of capital ui. For the second term here, uh, I'll describe it here, just a minute. Okay. So the second term, which is the convective term, is del uj del by del xj of ui. Now I can add ui del by del xj of uj to it, because this term as per continuity equation is 0, so I can certainly add 0 to it, and you'll get del by del xj of ui uj. Okay, now I'll write ui as the average part and the fluctuating part. Likewise for uj. Okay, so your sorry, ui uj would become, and if you take a time average of this thing, so the averaging process will be applied on all the terms on the right hand side. Now these velocities are averaged to begin with, so this will be simply ui uj. Okay, this on the right hand side, this term will come out, and then you have an averaging operation on the fluctuating part, and the average of fluctuating part would be 0, so this term will go to 0. Likewise, this term will also go to 0, and it'll be left with the time average of ui uj prime. Okay, so this is the second term here. You get uj del by del xj of ui for the mean velocities, and this term for the correlation of fluctuating components. Uh, Now what we'll do is we'll shift to this to the right hand side and write it in this way. So what I've taken here is I've taken the del by del xj operator common from both this term as well as the viscous term. Okay, so you have 1 by rho del by del xj of mu del capital U by del xj plus this term. Now this term is the viscous shear stress. Okay, so in analogy to that, we call this Reynolds shear stress. So when you average the momentum equations using Reynolds decomposition, you get an additional term on the right hand side here, which are called the Reynolds stresses, um, and the source of these terms are the non-linear term on the left hand side. Okay, so this equation here is called the Reynolds average Navier-Stokes equation, or the RANS equation, which is used for RANS modeling. And the modeling actually models this Reynolds system. So your UIUJ is modeled as a function of the mean flow itself. And using this model, they get an equation for the mean flow, and they solve it to get the mean flow itself. Okay, so that was the basics of these equations. Okay, I'll talk a little bit about the character of these Reynolds stresses. Okay, so on the left here we have an isotropic distribution of these UV fluctuation, this correlation. So these are individual U and V's. This point actually represents some U on this axis and some V on this axis. Now, if you have an isotropic distribution of UV, your average statistical average of that will be zero. Okay, but the actual turbulent flows are not, they do not have an isotropic distribution of UV. So the distribution is slightly skewed, and you get a slight negative value. So for turbulent flows, you get U prime V prime of negative of zero point 0.4. Okay, now an isotropic distribution actually represents that there is no directional preference to this flow. But in actual turbulent flows, we have this slight skewness. That is, there is a directional preference. So this also hints that there is some order to the flow. So turbulent flows are not entirely random or chaotic. There is a mixture of chaos and order to it. Okay, now we'll move on to the aspects of simulation and modeling. So we have seen the instantaneous flow equations and the mean flow equations as well for the momentum and continuity equations. Now there are these two terms called simulation and modeling. So what simulation actually means is that you're solving for your instantaneous velocities, okay, for all positions in time, while the modelings are okay. While the modeling term is used in when you actually model the Reynolds stress term and solve only for the mean velocities. Okay, so the simulations are, there is direct numerical simulation where you directly solve the Navier-Stokes equation using several methods like, spectral methods are there. You have finite difference and finite volume methods, and there are large eddy simulations as well. So in large eddy simulations, you do not solve for the instantaneous velocity. Instead, what you solve is for a filtered velocity field. Now, in this filtered velocity field, you actually remove the effects of small scales that are there in the flow. I'll discuss these what these scales are a little bit later in this lecture series. But what large eddy simulation does is it actually solves only for the effects that are contributed by large scales that are present in the flow, and it models the effect of small scales. We'll also see why this is done. Okay. Okay. This here is the okay. DNS actually solves for all the scales that are there in the flow. So we'll now discuss what scales are. So it is believed that turbulent flows they're composed of eddying motions. Eddying motions, as in if you plot the streamlines, you'll see circular streamlines there. So there have these streamlines will have a circular nature to them. So these are called eddying motions. Now these eddies can be of different sizes. Okay, and the size is decided by the region of influence of that that eddy. Now we can get an estimate of the size of that eddy by looking at the correlations. Correlations are these u prime v prime products averaged in time. These are called correlations. So if we look at these correlations, we can get an estimate of this thing. Okay. So how do these correlations give you an estimate of the size of of an eddy? So let's assume, let's say that this is an eddying motion here. There are 2 points inside this eddy, P1 and P2, and then there is another third point which is outside the region of influence of this eddy. Okay, we define two correlations here, R1 and R2. These are for velocities at point P1 and P2, and R2 is for point P1 and P3. So R2 is the correlation for the 2 points which are, they are not in the common influence of the eddy. Okay, now, so R1 would be high. So the correlation between these 2 points would be high because they have a common influence of the city. Okay, so if you see some fluctuation here, there will be a corresponding fluctuation here. So these fluctuations will be correlated in some sense. And as a result, you'll get higher correlation for R1. Okay, and a lower correlation for R2. Now, if we assign a size L to this eddy, let's say the diameter of this eddy would be L, then your correlations would be high if your separation between these 2 points, P1 and P2, that is delta x1 2, is lower than L, and it would be less if your separation is low. Okay, so how do we get an estimate for this size of the eddy? So what we do is we plot the autocorrelation coefficient as a function of the separation between these 2 points. So we take the correlation of velocity u at point x and the velocity u at point x plus r. So there is the separation of r between these 2 points. So you have u at x and u at x plus r. You take a product of these two fluctuations and normalize them with the RMS of u. So what you get is correlation coefficient. Now if you make a plot of this correlation coefficient with r, you'll get a curve something like this. Okay, so for when there is no separation, the correlation coefficient is 1, and as the r increases, the correlation coefficient drops and it asymptotes to 0. Okay, now if you integrate the correlation coefficient curve, you'll get an the value that you get is L. So L is basically the width of a triangle of unit height whose area is equal to the area under this autocorrelation curve. So this L is called the integral length scale, and it gives you a measure of the size of that eddy. Okay, so are we clear till now? I guess we are. So if you calculate the integral length scales for your velocities measured in the flow, it will give you an estimate of the large scales that are there. Because there are all the scales present in the flow, so there are large scales present as well. So your velocities will be correlated at least till that till the size of that scale. So if you measure the velocity in a turbulent flow and you calculate the integral length scales, that integral length scale will give you an estimate of the largest scales that are present in the flow. Now for small scales, we can get an estimate by using Kolmogorov's similarity hypothesis. I think, I mean, if you are not familiar with the research in turbulence, you might not have come across this thing. So I'll go slow from now on, and you can stop me anywhere if you have any doubt. Okay, so the small scales can be estimated using the Kolmogorov's similarity hypothesis. So what this says is, uh, when the Reynolds number is sufficiently high, the turbulent motions at small scales, that is okay, and this capital L here is the integral length scale, so I should write it here. Okay, so the eddies which are much smaller than the eddies, much smaller in size than the integral length scales itself, that is the small scales, are statistically isotropic. that is any directional information that is there in the flow is lost as you go to the smaller scales. uh, okay, what I mean by that is mm, okay, let's consider a jet for an example. So there is a jet issuing from an outlet, or let's talk about rockets. So we have a rocket here, and there is an exhaust jet from this rocket. Okay, now there are shear layers present at the edge of this thing. So there is a high velocity here, and the ambient is stationary here. So there are shear layer present at this interface and this interface. As a result, we see, the large eddying motions, or they're also known as coherent structures. Okay, these are the large eddies that are present in the flow. Now, if you take a section here and look at them planarly, they'll have shape, some toroidal kind of shape there. Okay, it might not be a full toroid, but it will have some shape. So it has some, you know, the shape of this uh, large eddying motion would be such that it will convect downwards. So it has a directional preference to it. However, the small scales, so as per the Kolmogorov's hypothesis, the small scales will not have any directional preference. So they might be oriented randomly. Okay, so this toroidal vortex would be in this plane itself, and it will convect downwards. However, at small scales, the first thing is the shape might not be the same; it might be different, and they may also be oriented in a random way. So there is no directional preference at small scales. So what it says is, at high Reynolds numbers, the small scales are statistically isotropic. Okay. Hope this is clear to you. Okay. Okay. So this is the assumption of isotropy, and there are two similarity hypotheses. The first one says that the small scale statistics, they have a universal form which depends only on your dissipation rate and viscosity. So what is this dissipation rate? We all know the kinematic viscosity, but what is this dissipation rate? Okay, so you know uh, in turbulent flows, the velocities are fluctuating randomly and violently. Now you can, from the fluctuating part, you can calculate the RMS of this fluctuating part, and or you can say that these random intense fluctuations, they have some energy to them. So this is called the turbulent kinetic energy of the flow. Okay, so this turbulent kinetic energy is being produced somehow. Okay, and the theory says that it is being produced at large scales, and then uh, it goes from large scales to smaller ones, where it is dissipated through viscous action. Okay, so you have turbulent kinetic energy being produced at large scales. So there is production at large scales. Now this goes to smaller scales, where it is dissipated. Okay, it is dissipated at small scales because the velocity gradients are much higher at smaller scales. So all the energy that turbulence has is being produced at large scales and dissipated at smaller ones. So the Kolmogorov hypothesis says that your small scale statistics will depend only on this dissipation. Okay. Okay. So from these two quantities, using similarity analysis, so dimensional analysis, we can estimate a scale for these small scales. Okay. I hope you all are familiar with the dimensional analysis itself. So the viscosity will have some dimensions of mass, length, and time. and your dissipation will also have some dimensions of mass, length, and time. And you have to use a combination of these two parameters to get a term which has dimensions of just length. Then the length scale that you get using these two terms is called the Kolmogorov length scale. Likewise, you can also get a velocity length scale and a time scale. Okay, so these Kolmogorov length scales are an estimate of the smallest scales that are present in the flow. Okay, so this is the so we've seen the first similarity hypothesis, which talks about scales which are much smaller than the integral length scale. Now, all the scales that satisfy this criteria are said to be in the universal equilibrium range. Okay. Now, there is something called inertial subrange. So uh, this is a second similarity hypothesis, which says that okay, your scales are much smaller than L. That is, your scales are in the universal equilibrium range, but they are still much larger than the dissipation range. So, if this condition is satisfied, the statistics of these scales would depend only on the dissipation rate, independent of the viscosity. Okay. So why this is so is because your scales are still much larger than the scales at which dissipation is happening, than the smallest scales in the flow. So there is no viscous effect here. Okay, but it depends on the dissipation rate because it has already been established by the large scales. So all the turbulence energy which is produced at these scales has to be transferred to the smaller scales, and this dissipation rate has already been established. So that is why it depends only on the dissipation rate. Okay, so this is the second similarity hypothesis. Okay. Now, okay, so both of these hypotheses say that your so your both these hypotheses say that your statistics are have some functional form. So, according to first hypothesis, your statistics would depend only on epsilon and nu, while in the inertial subrange, the statistics will depend only on epsilon. So, what are these statistics? Okay, so you have your instantaneous flow velocities, which are fluctuating in space and time. Of course, you can take a mean to get the mean velocities, which is the first order statistic. Okay, this depends on the large scales of the flow. Then you have your second order statistics, which are the RMS, correlations, and spectra. We'll talk about spectra in detail a little bit later. So these are your second order statistics. You can also have higher order statistics like your triple correlations or fourth order correlations. Okay, so uh, what the Kolmogorov hypothesis says is that your second and higher order statistics for the small scales, they will depend only on epsilon and mu. Okay, so we'll look at these second order statistics, that is correlations and spectra now. So earlier we had defined correlation coefficient where we normalized this term on the right hand side using the RMS of u. Now if you do not normalize, we have is just correlation. And if you take a Fourier transform of this correlation function R, what you get is spectra. So you go from spatial dimension to wave number dimensions. Okay, and this phi k and rk, they form a Fourier transform pair. So you get phi k by Fourier transform in the correlation, and if you take inverse Fourier transform of phi k, you get r back. Okay, so what Kolmogorov hypothesis says is your second order statistics, that is either these correlations. Okay, there are plots for these correlations as well, which I have not discussed. So Kolmogorov talks about structure functions, which are functions of these correlations. Okay, I'll be talking about spectra because it is easier to grasp. Okay, so your spectras are a function of these wave numbers. Now if you plot the spectra here, so Kolmogorov says that for scales which are much smaller than L, the inertial length scales. Now the corresponding relationship for wave numbers would be, for wave numbers which are much larger than KL. So KL is the wave number corresponding to the integral length scale, which is 2 pi by L. So for wave numbers much larger than KL, so let's say this is KL. So for all the wave numbers larger than this, your phi k will have a universal form. So this is the first similarity hypothesis. Okay. Uh, okay. So your we can define an energy density function ek from phi k. Phi k is a spectra, and ek is a special form of spectra which you can plot as a function of the magnitude of these wave number vectors. So these k here are the wave number vectors. Now you can reduce this. You can derive an energy density function from these spectra, which would be a function of your wave number magnitude of these wave number vectors. Okay, let me show you like this. So you have these k1, k2, and k3, your wave number space, and some distribution of your spectra. Now, for a constant magnitude of k, you'll get a sphere. Okay. Now, if you take an average of phi over this sphere, that average is E k. Well, k is the radius of this sphere. So we get a function for ek. Okay. Now Kolmogorov said that we'll get a universal spectra which depends only on epsilon and nu. Okay, so he derived an expression for ek which depends on epsilon, and the dependence on nu is through eta in this function k, in this function psi of k eta. Okay. Now in the inertial subrange, your ek cannot be a function of nu. Now the functional dependence on nu came through eta, so this says that your ek, so this functional dependence on psi will not be there. So your ek will become a function of epsilon and k, and the in place of that function psi we have this constant c here. Okay, so as per the second similarity hypothesis, in the inertial subrange, that is for length scales much smaller than L and much larger than eta, or in the wave number space for wave numbers much larger than KL and much smaller than L, you'll have a region called inertial subrange. And in this range, your spectra or the energy density spectra will have this form. Now, epsilon has already been established, so this one won't change, and your spectra will have a wave number dependence like this. Now, if you plot E and K on a log scale, it will have a slope of -5/3. Okay, so this is called the -5 third law, and it is well known in turbulence literature. Okay, so are we clear till now? I'll wait for your questions if you have any. Okay, so we were talking about DNS when we started talking about scales. I'll just show you where we were. Okay. So we said that your DNS can resolve all the scales that are there in the flow. So we started discussing what scales are so that you would have an understanding of what scales are. So your DNS can resolve all the scales in the flow. And how many scales do you have? You have from the large scales in the integral length scales to the smallest one, which are of the order of Kolmogorov length scales. So DNS can resolve all of them. Okay, so now that we have discussed about the length scales, we are back to DNS. Okay, so DNS is used to resolve all the wave numbers. However, it takes a lot of computational effort to resolve all of them. So what LES, that is large eddy simulation. So it only simulates the large eddies. That is why it is called so. It it uses a cutoff wave number KC and simulates only wave numbers smaller than KC. So there is a cutoff wave number KC here. So it simulates only wave numbers smaller than this and models all the wave numbers larger than this. Okay, so if we have time, we'll discuss a little bit. Mm. Okay, so we'll start our discussions on DNS methods that are there. Do you want break? We can take a break for about 5 to 10 minutes. Anyone?
I think it should be at tea time, na? 4 o'clock,
Sorry.
around 4 o'clock.
Yeah, but I think if you go for a tea, it will take a long time. And if you want to break for a few minutes, I can stop. Otherwise, you might have to
So just a
sacrifice
question,
tea
Adit.
for.
Just a question, Adit. You
Yeah,
said that DNS resolve all the length scale. Is
yeah.
there is any provision to provide that key length to provision to provide the length scale? Just like you see, na, in LES, now we say we have a cutoff length scale KC.
Yeah.
It resolves more than all the length scale greater than the KC. Just like that, how we are going to provide that these are the length scale in our course?
Okay. Okay. So when you do DNS, usually you know what Reynolds number you're going to simulate it on.
Yeah.
So you have Reynolds number as an input. Okay. When you have Reynolds number, okay, if I don't know if you know, I have not told this, but your Kolmogorov length scales are a function of Reynolds number. So, okay, so your eta by L is a function of Reynolds number. Okay, so you will once you have your Reynolds number, you'll have an estimate for uh, what your Kolmogorov length scales are going to be. Because when you start DNS, you have your Reynolds number and you also have your domain size. Usually, your integral length scales are of the order of your domain size. Okay, so from these two, you can get an estimate for integral length scales. And when you discretize your domain, so let's say if you use a step size of delta x, or you use n grid points, so your delta x would be L by n minus 1. Okay, so your delta x should be of the order of eta. Okay, so usually in simulations, your delta x is about some multiple of eta, 5 eta, 2 to 5 eta. So for my simulations, I had it from 2 to 5 times eta. Okay, and it's been found in studies that your dissipation peaks at around 12 to 15 times eta. So it peaks at these scales. So does that answer your question?
Yes. That's right.
Uh, uh, so let's take a big break for 5 minutes. You can go to washrooms and
Sure.
okay. Okay, so are we back? Okay, just tell me once you have all joined again. Hello.
Yes, we can
Yes,
start
Bhavya.
now.
Can we start now?
Yeah,
Okay. Deshik, are you here? I guess Deshik is not here.
Yes, yes. Yes, I'm
Okay.
here.
Okay, we'll start now. Okay. Okay. So to perform direct numerical simulations, we have a few methods. We have pseudo spectral methods and we have finite differences. There are also finite volume methods. So we'll be discussing these two, pseudo spectral and finite differences. Okay. So your in compact 3D, the open source code that we'll discuss is a finite difference code. And We'll discuss an open source database as well, which is John Hopkins Turbulence database. Okay, so it has databases for several simulations. There are a few forced isotropic turbulence simulations, few channel flow simulations, and transitional boundary layer simulations as well. So I think yeah, they are pseudospectral simulations. So we'll start with pseudospectral method. Now this method has, it has better accuracy than finite difference methods, because for finite differences there are the differentiations are not as accurate as you get for uh, you know in spectral methods. Now this was pioneered by Orzak and Patterson. So this is a paper you can refer to, and also improved later by Rogallo. Now these are preferred when your domain is, when you have a simple domain, like let's or cubical, or when you have a simple domain or rectangular, simple domains like this, and where your boundary conditions are homogeneous, because in your spectral methods you'll be solving your Navier-Stokes equation in Fourier domain, and for your Fourier transformation process, your boundary conditions have to be homogeneous. So these are the two conditions, and in this thing the Navier-Stokes equation is solved in Fourier space. So what we do is we solve for UKT. Okay, we get the velocities in Fourier domain, from where you can take the inverse Fourier transform and get the velocities in spatial domain. Okay, so for that we'll start by looking at what the Navier-Stokes equation is like in Fourier domain. So for that we'll take the Fourier transform of the entire Navier-Stokes equation, and we'll look at all these four terms one by one. So your first term is, it's the time derivative of velocity. Okay, we are Fourier transforming in space, so this operation will commute, and you'll get the gradient of time derivative of your ui hat. So hat is used to represent the Fourier transform of that quantity. Okay, then you have your convective term. When we take the Fourier transform of that, uh, so uj del by del xj ui is written as this term here. We had seen earlier how this term comes about, and for now we'll call it gi hat. Okay, we'll look at it later, in depth later. Now the third term is the pressure gradient term, and you know if you write the Fourier transform of p by rho as p hat, so this term is the spatial gradient of p by rho, and you might be knowing that if the Fourier transform of some function p is p hat, then the Fourier transform of the derivative of this term would be I k times p hat, I wave number times p hat. So you get the Fourier transform of pressure term as this term. Okay, and then you have your viscous term. Okay, so when you differentiate one, you multiply it with I k. When you differentiate twice, you multiply it twice. So what you get is nu. There are two i's. These are complex square root of -1. So this will give you a -1 here. So you have negative mu, and then you have kj dot kj. Now these are in, if you remember, these are in tensor notations, and these repeated indices will give you summation. So your kj dot kj is, so your kj dot kj is basically k1 square plus k2 square plus k3 square. So this is basically square of the magnitude of wave number vector. Okay, so we'll write the magnitude of wave number vector as simply as k. So we have this term is negative mu k square ui hat. Okay, so the Fourier transform of ui. Okay, so the equation in Fourier domain can be written like this. So for the time derivative term, you have this term. For the convective term, we wrote it as gi. For the pressure term, we had got minus I ki p hat, and for the viscous term, we got this. Now we'll rearrange it like this. We'll bring the viscous term here, and the g will take it to the right hand side. So we'll get this. Okay, so now we'll take the dot product of this equation with ki. So on the left hand side, we'll get you'll have del by del t of ki dot ui hat. Again, I have commuted this ki with del by del t operation, and you'll get mu k square ki ui hat. Now your ki ui hat is basically Fourier transform of this. Okay, again, so your Fourier transform of ui is ui hat. Okay, then your Fourier transform of del ui by del xi. This is the continuity equation, which is 0. This would be I ki ui hat, and since this is the Fourier transform of 0, this would be 0. So your I ki ui is 0. So your LHS identically goes to 0, and what your RHS becomes is you have I times ki square. So again you have ki dot ki, which is summation over repeated indices. Then this will become the square of the magnitude of wave number vector. So you have I k square p hat, and this would be equal to negative ki gi. Now this essentially is the Poisson equation in Fourier domain. Okay, so yeah, if you take the I to the right hand side, okay, I shouldn't have done that. If you take this to the right hand side, you'll have the IKI. And if you balance signs, you'll get this equation. So this term is basically Fourier transform of negative del square p, and this would be Fourier transform of the gradient of g, because this multiplies g with ki. So this is basically gradient of the convective term itself. Okay. Now we can solve this equation to get an expression for pressure. Okay. Okay. So before we do that, we'll take a slight detour and look at something. So this G is, we'll use it for a Fourier transform of the convective term, but for now you can think of this as some mathematical vector, as a general vector, not just that specific term that we had used. Okay, so let's consider a domain of that this wave number vectors k1 and k2. So we have these two perpendicular bases, k1 and k2, and um, your wave number vector is this. You have this k vector, and this random vector g hat will have a component parallel to this k vector and a component perpendicular to this k vector. We'll look at the expression for these two components. Okay, so this k is your wave number vector, and let e be the unit vector along k. So e would be your k vector divided by the magnitude of wave number vector. Okay, so your component parallel to k would be, and you'll get that by taking a dot product of g with the unit vector along k. Okay, so this gives you the magnitude of this parallel component, and again you multiply it with e to give the direction. Okay, so instead of e, you can write it as k by k, k vector by k. So this gives you an expression for the component which is parallel to the component of g, which is parallel to the wave number vector, and the component which is perpendicular to this vector can be obtained by taking the difference between these two. So you get g minus this thing. Okay, now let's look at the component parallel to the wave number vector. So if you take the jth component of this, okay, let me elaborate on this one. So we had k dot g by k square. Okay, so we have g parallel as k dot g by k square. And these are vectors. Okay, so k dot g is not going to be it will be a scalar. Okay, so this is k1 g1 plus k2 g2 plus k3 g3. Let me write it. Okay, uh, when you divide it by magnitude of the wave number vector, you have k square. Okay, and when you multiply it with the vector, so this entire scalar I can write as, let's say, a. So this is a times k, or a times k1i, k2j, k3k. So your component parallel to your jth component for this parallel part would be a times the component in the jth direction, k2, or let's say kj. Okay, so this would be kj times k1 g1 plus k2 g2 plus k3 g3 divided by k square. Now this is a summation here, so I can write it in tensor notation. I can write it as kj kigi, and we have the wave division by wave number, square of the wave number. So we get gj, jth component for the parallel part, as ki kj gi by k square. So this is what is written here. Instead of I have taken another index k here. Okay, so this repeated index is basically the summation. So it does not matter if you use I or some other symbol, you can also use M here. Okay, now we'll look at the perpendicular part. So likewise, if you look at some jth component for this, for the perpendicular part, we'll have jth component for G minus the jth component for the parallel part. Now, if you want to take gk common out of this thing, I'll write this gj as gk times delta jk. So delta is, this term is 1 only when j is equal to k or k is equal to j. So this is basically equal to gj. Now if you take gk common out of it, you'll get delta jk minus kj kk by k square. So this term in the bracket is basically the projection tensor pjk. Okay, so your pjk is delta jk minus kj kk by k square. So if you multiply the projection tensor to a vector gk, you'll get the component of this vector along the wave number vector using this equation here. Okay, so this was just to show you the expressions for the parallel part and the perpendicular part. Now we'll come back to this Poisson equation here. So this we can solve by taking the ik square to the right hand side. Okay, so you'll get pressure term as minus 1 by I. So instead of ki gi, I am not writing as km gm, because again repeated indices is a summation, so I can replace it with m. Okay, so this is the expression now. Now if you remember the pressure term, it was this term. So it is minus I ki p hat. So we'll now evaluate this one. Okay. So we have p. We'll get I ki times p hat. Uh, okay, minus I ki times p hat, and this would be equal to, this would be ki ki km gm by k square. Now, if you remember the expression for the parallel part, kj kk gk by k square, this is the jth component of the parallel part. So this is a similar expression, and this is basically equal to the ith component of the parallel part of g vector. Okay, so what this shows is your pressure term, uh, that is the gradient of pressure. So this is basically the Fourier transform of this term. Now this equation shows that your pressure term exactly balances the parallel part of the convective term in Fourier space. Okay. Okay. So now we'll come back to the Navier-Stokes equation that we had. So we had the time derivative term, the convective term, pressure term, and G term. Okay. Now this pressure term balances the parallel part, so you are only left with the perpendicular part now. Okay, and this is this the we got an expression for the perpendicular part as uh, for the ith component. Okay, so for the jth component it was pjk gk, and for the ith component it would be pij gj. Okay, so uh, that's that. Now we have the Navier-Stokes equation, the Fourier domain. Okay, so how to solve this? Okay, once you have the initial condition, which is your ui, you can evaluate this term, you can evaluate this term, and then use this term to get your ui hat at next time step. So you can solve like this. Okay, we still haven't looked at this term gj, or the g hat itself. So we'll look at this now. Any questions till now? Because this was a bit complicated, I guess.
Yes, it was a bouncer over my head.
Yeah, yeah.
I
Okay,
understand pressure poison equation, but certainly involving FFT in that, na, it's create a complex.
okay. I can repeat some parts of it if you want.
No, no, no. Don't repeat. Na, it won't be any good because na, we are involving two to three different things. Na. Pressure poison equation is one thing.
Uh-huh.
Doing FFT and involving that and completely transforming everything. Na, it's a certain
Yeah,
complex mathematics.
yeah.
Na. It will
It's
take
not
time to
yeah,
digest.
it's not usual to see it like this. We have been seeing it in
Yeah.
real space only. Anyways, yeah, you can always come back to the recordings, or you can also talk to me if you have any doubts left.
Yes, yes, yes.
Okay. So we'll move on now. So we'll look at this GJ term, which is the Fourier transform of convective term here. Okay. So GJ is the Fourier transform of this term. Okay, so the spatial gradient is involved, so this will come as the ik times the Fourier transform of uj uk. Now, for uj and uk, I'll write them as Fourier expansions itself. So for uj, let me use these colors now. For uj, I have this expansion in terms of Fourier coefficients. Uj k prime, ei k prime dot x summed over all wave numbers. So this is the Fourier transform, Fourier series expansion of uj. Likewise, we have Fourier series expansion of uk. We have used, okay, so these have to be independent, right? K prime and k double prime. So we have used separate notations for these two. Okay. Now When you take Fourier transform of something, so let's say you have function ax. If you take a Fourier transform of it, you multiply it with e to the power I k dot x, sum over all k, and you get the Fourier transform of this as ak. So the Fourier transform operation is basically taking product with e I k x and averaging and summing over all of them. Okay, so the Fourier transform operator that we had here is now applied here. So we have this product of e to the power negative I k dot x, and these brackets here are the summing operations there. So this is basically the correlation. So look carefully what has happened here. You have these summations over k prime and k double prime. I've taken the product of uj and uk. So these are here. Your these two exponential parts are here. Your ei k prime plus k double prime dot x, and this extra part is because of the Fourier transforming operation. Okay. Okay, so now we'll look at this part itself. Okay. You have your e to the power I k prime plus k double prime x dot x, and e to the power minus I k dot x. You're basically taking a correlation of these two. Now, if you remember, Mhm. Okay, think. Hmm. I mean, this term will survive only when your k is equal to k prime plus k double prime. Okay, because these waves are orthogonal to each other. Okay, I thought maybe I'll give you a derivation of this, but I had not prepared for it. So maybe some in the next class or something. But these term will survive when your k prime is equal to summation of k. So your k is equal to summation of k prime and k double prime. Okay, so that's what has happened here. This term is written as delta of k and k prime plus k double prime. So only when these two are equal, you'll have unity here, and now you have an expression like this. Okay, so now instead of k double prime, I'll write it as k minus k prime, and instead of using two summation symbols here, I'll just use the summation over k prime here. So I get an expression for gj kt as this. Okay, and I use this in the Navier-Stokes equation itself. So it was the Navier-Stokes equation was the perpendicular part of gj. So it's pijk times gj, and from the gj the ik part is here. This is the summation part. Okay, so this is a very complicated equation here. On the left hand side you have your time derivative and viscous term. On the RHS you have this complicated term which has the velocities are have contributions from wave number k prime and k double prime. However, the entire right hand side has contributions from all three k prime and k double prime. Okay, so this term in wave number space, the convective term. So this is the remnants of convective term after the pressure cancellations. So these are non-linear and non-local. Okay, so it has, so if you choose, it's not like you're solving only at a time you're only solving from k for one k. You have effects from other k's as well. Okay, so if you choose, uh, so if this is k prime, if you choose some k double prime, you'll have to consider k. which is dependent on this one. So this is non-local as well, and this involves triadic interactions. So triadic interaction is basically, contributions from three wave numbers. Sorry, k prime and k double prime. So there are three wave numbers. That is why this is called a triadic interaction. It is this is an important term when you start studying, turbulence energy cascade, even in LES, where you cut off your simulations at some wave number. Okay, so what is happening here is, uh, you have interactions across the spectra. So this k might be interacting with some wave number here, but if you cut off your simulation at this kc, these interactions are not accounted for. So these have to be modeled. So these models have to include these triadic interaction terms. So these are studied as well in research problems. Okay, so what spectral methods often do is they calculate the convective term in the physical domain itself. Okay, they calculate this thing. They calculate the this entire. Oh, I'm sorry. I'll fix it later. Yes, it was. Okay. Anyways, yeah. So this term is calculated in the physical domain, and then we take a Fourier transform to get GJ. Okay, so that's how spectral methods work. Because it is complicated to compute the right hand side. Also, it is computationally very costly. Okay, so they calculate it in real space and then take a Fourier transform. And because of this one calculation, these spectral methods are called pseudo spectral methods, because not all of it is happening in the spectral domain. Okay. Uh, so how do you go about performing your DNS? So you first decide the size of your domain. So you can decide to do the simulations in a cubic domain. So this cube might have a size of L by L by L. So your domain size is of order L. You might decide to have n wave numbers in your spectral domain. Okay, so your largest wave number that you would resolve will have a wavelength of L. Okay, so your largest wave number will be 2 pi by L. Now you can choose to have your wave numbers would be a multiple of this smallest wave number. Okay, so you can define your wave numbers in this manner, where your wave number vector is k naught times the n vectors. Okay, so n vector is basically e1 e2 e1 n1 e2 n2 e3. These are the unit vectors in the three directions, and your n can go from minus n by 2 plus 1 to n by 2 plus to n by 2. So n is the number of wave numbers you want to resolve. So this is the smallest wave number, and for the largest wave number, your largest wave number is going to be half times n k naught. So this will come out to be pi times n by L. Now, if you want to look at what the equivalent resolution in space would be, delta x in space would be L by n. So L by n would be, from this equation here, it would be pi by k max. Okay, so this is delta x. The smallest wave that you are resolving, 2 pi by, so the smallest wave you are resolving has, wavelength of 2k max. So, this width, twice of this width would be the wavelength of the smallest wave. Ah, this you can also write as 2 delta x is equal to 2 pi by k max, or k max is equal to 2 pi by 2 delta x. So, the wavelength corresponding to the highest wave number is 2 delta x. So, if this is your delta x, the wavelength of the smallest wave number will be twice of this. Okay, so that was some basics of it. Again, these resolutions will depend on your Reynolds number. Okay. Okay, so your Reynolds number will give you the k max. Okay, because the spectra depends on your Reynolds number. So this is your k max. You'll get your k max. From your k max, you can get your n. So you have L, you have k max from the Reynolds number. You can have an estimate for the number of wave numbers you'll have to resolve. Okay, so you have two inputs, L and RE. RE gives you k max, and this gives you the number of wave numbers to resolve. And then what you're left with is the coding part of it. Okay, so we are done with the pseudo spectral methods. Okay, these are for homogeneous boundary conditions. Okay, let me just see. Okay, so your let's say your homogeneous and isotropic turbulence simulations. Your boundary conditions are periodic in all three directions. So in x, y, and z. So these boundary conditions are homogeneous. Let's say if you want to perform channel flow simulations. So you have a channel. This domain would be limited, of course. Your channel has a length of L, height of 2h. So this is h. The total height is 2h. And it will have some width as well. So width is z. Now the channel flow, you can have homogeneous boundary conditions in x, and you can have homogeneous in z. In the y, at these walls, you have the no slip condition. Okay, so your velocity has to be 0 at these 2 points. So you cannot expand your velocities um, as a Fourier transform in this direction. So what people do is they use Chebyshev transform for this y direction, and then they solve. So I don't know too much details of how this is done, how the channel flow simulations are done in using pseudo-spectral methods. I mean, if you are interested, you can go into the depths of it. What I've done is uh, for the for cases like this, like for channel flow or for boundary layers. Okay, for boundary layers, there is no, so the homogeneity in x also is lost. So this is homogeneous only in z direction. It's not homogeneous in x and y. Okay. Okay, so the method I'll be talk. So for these, uh, I'll talk about incompact 3D, which can incorporate these simple domains, and also it can as the geometry gets even more complicated, the spectral methods become more and more difficult to apply. So that's when the finite difference methods become relevant. Okay, so even yeah. Okay, so we'll start by discussing the finite difference methods. So in these methods, what we do is we approximate our derivatives using finite differences. Now, the associated differentiation errors are higher in this case. Okay, so um, okay, I'll talk about this, what these errors are and why they're higher later on. But how finite differences approximate these velocity derivatives. Like for example, here we have you know here the first derivative of y with respect to x is approximated using forward Euler and backward Eulers. So these are all first order methods, and you have some associated errors. So for first order methods, your associated error would be of the order h square, right? No, yeah, I guess. Okay, let's check. So these methods, how do we get these methods? These difference approximations are evaluated are formulated using Taylor's expansion. So if you had to derive one of them, so let's say you want to look at how the forward Euler has come through. So what you do is you look at the Taylor's expansion y about x. So this would be y of x plus h times dy by dx plus h square by 2 factorial d2y by dx2 cubed by 3 factorial, and you have your higher order terms. So what we want is dy by dx. So you can get dy by dx as y of x plus h minus y of x by h minus these higher order terms. So this would be h by 2 factorial dy by dx d2y by dx2. Okay, if you take 1 by h out here, this would be h squared by 2. So the entire term would be the same. Okay, so this is the forward Euler approximation, and the error term can be written as 1 by h dh squared. So this gives you a second order, first order accuracy in it, and your errors are second order in h. So if you can write it in this form, this is called to have second order. First, the errors are called to be of second order. Likewise, for central difference scheme, you'll have the error which is of the form e to the power h 4. Let's see. I shouldn't have forgotten these. Okay. So for your second central difference, the error term is of the form 1 by h p of h cube. So this is a second order scheme where the leading order error term is of the order of h cube. Anyways, so what I meant is you can approximate your derivatives using these finite difference schemes, and then solve your ODE or PD like this. So you approximate this as a finite difference, uh, and then you have your values at T1 through initial conditions, and then you get your values at T2 but using this equation. So this is an approximation here. From this you get an expression for y at T2, and then subsequently again you can use the same approximation to get y at T3, T4 and further. Okay, so this can also be applied to your Navier-Stokes equation, which we have here. So what you do is you send the convective term to the right hand side. So we have it here, and then we have an equation like this. So your del u by del t is equal to this expression. Now this expression is evaluated at time t. So you have your initial flow field, which is the initial condition, which is your initial and boundary conditions. So you evaluate the right hand side, you approximate the left hand side using finite differences, and then you get the solution at time t plus delta t. And then you keep solving iteratively to get your solution at Tn, this time t plus n times delta t. So that's what principally this is. Okay, so now we had so essentially we have to discuss in compact 3D, which is a sixth order finite difference scheme. Okay, so before we start discussing this, we'll look at a paper by Sanjeeva Lele, which discusses several finite difference schemes and their associated errors. Okay. Okay, so we'll move on to Sanjeeva Lele now. Okay, so these are compact finite difference schemes with spectral-like resolutions. Okay, so when we approximate using finite difference schemes, there is some truncation errors. So there are those error terms that are left out when we approximate are called the truncation errors, and because of that, what happens is there are some wave numbers which we cannot resolve, and as a result, the our schemes are not as accurate as spectral differentiation would be. So these compact schemes are, they have a higher order of accuracy. That is, their truncation errors are small, and their accuracy is compared with spectral methods to see how close they are to those. Okay, so we'll first look at the approximation of first derivative. Okay, so you know, so it uses this general form of expression to approximate your derivatives. Okay, so these f primes are first derivatives of these functions. Okay, and let's say you want your derivative to be at ith point. So this is what you want, the derivative at ith point. For that you need to have your derivative at I plus first point, I plus second, that is a point ahead of you. So let's say this is your domain. You have I plus 1, I plus 2, I minus 1, and I minus 2. So as per the scheme, you have to have derivatives at all the neighboring points, and this is equated to this expression here on the right hand side. Now the right hand side has terms at I plus 1 and I minus 1, plus 2 and minus 2, and plus 3 and minus 3. So you need 3 points ahead of this thing, plus 1, plus 2, and plus 3. So in all you need 7 points, information at 7 points to evaluate these family of methods. So as per this expression, what you get is a family of finite differencing schemes. Okay, so you can change these parameters alpha, beta, a, b, and c, and get several schemes of varying degrees of order. Okay, so you have uh, so if this is the relationship between your ABC and alpha beta, you get the second order differencing scheme. Likewise, fourth, sixth, eighth, even 10th order schemes here. Okay. So the scheme that Incompact 3D uses is a sixth order scheme. It's this one. It has beta. It's the one with beta equal to 0. Okay. Let's see. Yeah. The sixth order tridiagonal scheme 2.1.7 is a member of this family. So it has beta is 0, alpha is 1 by 3, c is 0. Uh, okay, there must be an expression for b and a and b as well. A is 14 by 9 and b is 1 by 9. Okay, so likewise there are other schemes as well. You can also have you can also approximate the second derivatives using again a family of these finite difference schemes. Here also you have several schemes of varying degrees of order. Okay, so what we'll now look at is the Fourier analysis of errors. Okay, so let's give you some background of this. Okay, so the Fourier transform of the derivative of u is I k times the Fourier transform of u, right? Or I k times of u hat. So I can get the derivative by taking the inverse Fourier transform of this thing. Okay, now let's say we have approximated a derivative del u by del x using some finite difference scheme delta u by delta x. This gives us, let's say, u prime fd. Uh, if you take the Fourier transform of this thing, you can write it in an analogous form like some I times a modified wave number k prime times u hat. So for the actual derivative, you have I k times u hat, and when you take the finite differences, you can have an analogous expression like here. So, but you'll have a modified wave number k prime. Okay, so how different this k prime is from k will quantify this error that the finite difference scheme differencing scheme has brought about. Okay, so for this, what they do is they plot k prime by k as a function of k. Okay, so we'll go back to this paper here. So this is what they have plotted here of k prime by k, the modified wave number k prime by k as a function of k. So you see for low wave numbers at k, sorry, this is not k prime by k, but just k. Okay, this is k prime. So the modified wave number. So at the low wave numbers, you have your k prime is equal to k. See, more or less equal to k. But you start seeing some deviations from the ideal at higher wave numbers, and this is present at all the schemes. But you see the deviation, result scale. So I mean, if you define a tolerance as to how much it can deviate from this ideal diagonal line, so let's define a tolerance of plus minus e or plus minus e by 2. If it deviates from this, let's say this method here, it deviates from the ideal at this point, so we can say that it resolves all the wave numbers smaller than k1. Okay, so we see that the wave numbers that are being resolved increases as we go from lower order methods to higher order methods. So let's look at all these methods here. Okay, so A is the a second order central difference. Okay, so it does not resolve as much. B is the fourth order Pade schemes. Sorry, for fourth order central difference. Let's have a pointer. Where is the pointer? Okay. Anyways, okay. So B is the fourth order central difference scheme. Here C is the sixth order scheme. So you see the resolved wave numbers, they increase as you go up in your resolution. However, you'll see that with 10th spectral like pentadiagonal scheme. Let's see I is 3.116. Okay, so look at the ith scheme. It is a spectral like pentadiagonal scheme. So out of all of these, this is the most accurate in resolving the wave numbers when compared to the Fourier differentiation. And if you look here, the spectral like scheme, it has a formal accuracy of fourth order. Okay, so ideally your the wave numbers resolved, they it gets higher and higher as you go from lower order schemes to higher order schemes. But you can you can get a you can resolve higher number of waves by just tweaking these parameters, tweaking these alpha, beta, a, b, and c. So you can look at how the resolved wave numbers change. Although your order of the scheme may not be as high, but you can resolve a higher number of wave numbers. Okay, so that's what the modified. That's how the differentiation error is quantified here. Okay, so this was for first derivative approximations. Okay, so this plot is again for spectral like schemes. You see, by tweaking those parameters, they can have any kind of behavior for this modified wave number. Okay. Uh, Okay, so one thing that you'll look at here is there are two kinds of errors here. When you use finite differencing schemes, you have dissipative and dispersive errors. Okay, so you have dissipative and dispersive. So what dissipative errors do is, you know, let's say this is 0. So ideally, the exact solution for this would be u is constant. So u at time t2 by u at time t1. Let's call this a gain function. This would be 1. This is the ideal thing that it should be. But for dissipative errors, what happens is, as you keep running the simulations, you'll see that the numerical solution, the gain function is less than 1. So that is your value eventually dissipates. Well, it won't happen in this case, but this is the character of dissipative errors. It actually reduces the energy at some wave numbers. So that is why at higher wave numbers these dissipative errors are higher here, and you see this behavior. Likewise, the dispersive errors are likewise there are dispersive errors. So now, how would you understand dispersive errors? Okay, so let's say you have a wave equation del u by del t plus c times del u by del x 0. So what this means is the solution for this would be that there is a disturbance which is traveling. Okay, so this is u x t. Let this be a function f x t. Now, if you look at the Fourier representation of this, it would be f times k t. Okay. Now, the thing is, as per the finite difference scheme, uh, the different wave numbers here will have different speeds in the solution here. So what will happen is this solution ideally it should it should travel from this point to this point without any distortion. But because of these dispersive errors, you'll start seeing uh, these wiggles at the edges, because there are these high wave number fluctuations would have higher speeds, some would have lower speeds. So these wiggles will start appearing in your solution. So these are called dispersive errors. So for that, what they do is they look at the wave speeds, the phase speed. So here they have plotted the dispersive errors for all these schemes. Again, you see the dispersive error is very lower for the case I. I is again the spectral like pentadiagonal scheme 3.1.6. Okay, so this was some discussion on the finite difference schemes that are there and the errors that are associated with it. There is something called aliasing error as well. Okay, let's look at aliasing error also. So this is there for both the spectral schemes and finite difference schemes. So what happens is, let's say your solution has, uh, or let's say your simulation is resolving the maximum wave number k, but your actual physical phenomena might have wave numbers larger than this one. Okay, so what's happening is, uh, this is the highest frequency you can resolve, but there are frequencies higher than this present in the flow. So what will happen is, the this green wave will, it will appear it will alias itself as a wave of a lower wave number or some other wave. So it will appear as a wave uh, of a lower frequency. Okay, so when you're unable to resolve all the wave numbers, if there are wave numbers higher than your resolution present in the flow, then you will see these aliasing errors. Okay, so these are the three kinds of errors that are present here. Uh, okay, it's 4:16 now. Do you all need a break or should I continue? Let's continue. So we are going to look at incompact 3D now. Okay, so this is a paper that describes the numerical scheme used by code and a few example cases simulated by the code itself. Okay, so and it's a finite difference, sixth order finite difference code. It can do both DNS and LES. It can also, it uses something called immersed boundary method. So you can simulate boundaries across which there is no flow. Like you can put a cylinder in a channel, so there will be no flow in this solid body here. So you can simulate this using the immersed boundary method. Okay, and this code finds its use when your geometry gets a bit complicated. So for simpler geometries, you can use Fourier methods, but this incompiled code can be used for complicated geometries. So it says it can be in non it can be used to do studies in non-academic geometries. Anyways, we'll start looking at the equations and the numerical scheme it has used. So this here is the Navier-Stokes equation with the convective term on the right hand side. Okay, so they have used what is called the skew symmetric form of the convective term. Okay, and they have used this because it reduces the aliasing errors uh, uh, in the numerical scheme. Okay, so you have the pressure term, the convective term, the viscous term, and if there is any forcing in the flow. This is the continuity equation here. So how do they solve this thing? So at kth time step, they calculate Fk. What is Fk? So Fk is your convective term and viscous term evaluated at kth step. So they evaluate Fk at kth step, F at kth step, and at k minus 1 step. They use a weighted average for these two, pressure term and the forcing term here, and they get an intermediate velocity field U star. So they've used the pressure at the previous time step to get velocity. You'll see that in this F term, it takes the contributions from the viscous term, convective term and the viscous term. The forcing is considered here, um, and the pressure is considered here to get an intermediate velocity U star. Now they have to also satisfy the continuity equation, which they enforce by using by satisfying the Poisson's equation. Okay, so I mean If you take a gradient of this momentum equation, the del dot u is 0, and you will get the Poisson equation of pressure in the physical domain that we had seen earlier. Okay, let's remove all of this. Okay, so the continuity is enforced using the Poisson's equation. So from u star they get a modified value of u double star, from which they calculate, from u double star they get pressure at pk plus 1. So this is the Poisson equation which they are enforcing to satisfy the continuity equation at k plus 1 step. So the velocity field that you get should satisfy this. This is basically this equation, and your del dot u double star should be evaluated. So once you have your u star from the first equation, from the second equation which takes the pressure at the previous time step as an input, you'll get your u double star. Now that you have your u double star, this will give you the pressure field at the next time step. Okay, and from this pressure field you apply a correction to this u double star again, and then you get your velocity at k plus 1 time step. So this is the numerical algorithm they have used. uh, this they call the fractional time step method. I think they might have mentioned it somewhere. Mhm. Okay, I don't know, I think they are not. Anyways, so this was the numerical scheme. Now you have to see how the boundary conditions, the initial conditions, the derivatives are evaluated, time and space derivatives are evaluated. Okay, so for simple domains, you have your um, either Newman or Dirichlet boundary conditions. So Dirichlet is you specify velocity at the boundaries. Okay, uh, and the Newman is that you specify the velocity derivatives. And let's say if you have a solid surface where there should be no penetration or no flow inside, for that they have used some. For that they use forcing to to specify the velocity zero there. So what they do is they use immersed boundary method, and they impose a target velocity in those regions. So if you have a cylinder in this channel flow, you can impose a target velocity of zero in this region. Okay. Uh, For that, they have defined a forcing term as follows. Now, when you're inside the solid body, your epsilon is 1, and elsewhere your epsilon is 0. So outside the body, there is no forcing. However, inside the body, the forcing term is written as follows. Okay, so if you use this forcing term in these numerical scheme, in these equations here, what you'll get is your uk plus 1 will be equal to the enforced velocity. So it enforces the velocity that you're specifying inside the boundary. Okay, so you can specify these um velocities inside the boundaries as well, inside the solid bodies as well. Okay, so for the spatial discretization, as I've told you, it uses the sixth order scheme from described in Sanjeeva Lile. As I told you, the beta was 0 there. So you have alpha, A, and B. C was also 0. So alpha is 1 by 3. Okay, sorry. Yeah. So alpha is 1 by 3, A is 14 by 9, B is 1 by 9. Uh, Also, they have used for the second derivative, they've used alpha of 2 by 11, A of 12 by 11, B, C. Um, okay, they have also derived the expressions for modified wave numbers. Okay, one thing, since these expressions they need data from a point before and a point after. At the edges, these expressions do not cannot be applied. So for the edges, uh, we have these expressions here. So you can calculate the derivative at edges using these expressions. So these. Okay. Yeah. So for the pressure, they have used a staggered grid. So for that, so let's if this is the if this is the computational grid, they solve for pressure on the staggered grid as shown as marked by red by me. On the right hand side, it is these hollow circles. So it solves for pressure here, because okay, because it does not say why, but it was proposed by someone. It has been proposed to use a staggered grid. Mm, if you want to know why, because there is some coupling issues that happen when we use q symmetric forms. Okay, let me see. Which one was it? Okay. Okay. So what happens is when you use skew symmetric form of the convective equation, uh, there are problems of decoupling. Yeah. So there are some problems that arise when you solve the Poisson equation for pressure. So this can be avoided when you use a staggered grid. Okay, to get into the details, you can refer to these references. So that's why they have used a staggered grid for pressure. Okay, visualize it. Okay, so what they do is they use interpolation schemes to get pressure at these points. They solve for pressure at the next time step, get the corrected velocity, and again uh, get the pressure at these points, interpolate to get pressure at the actual grid, and get the corrected velocities at these grid points. Okay, so there is interpolation involved as well. Okay, so the paper will describe the uh, differentiation scheme for pressure and the interpolation schemes as well, their modified wave numbers. Okay, uh, there is some description on how the errors propagate from boundaries to the domain. So on the at the edges, you cannot use the exact the higher order scheme. You'll have to use another approximation. So at the edge, there will be at the edge of the domain there will be higher errors. So you can go through that as well. It describes the numerical procedure of pressure treatment. So it solves for the pressure in the spectral domain. Okay, yeah. So it solves the Poisson equation in spectral domain. So because we had seen that in spectral domain, it was I k I p hat is equal to k square gi, or no, or something in service. K square p hat I k I g I. So your spectral domain, it is simply you know multiplication and division using wave numbers. So they solve for Poisson equation in spectral domain. Okay, so here it says the solving the Poisson equation consists in a single division of each Fourier mode by a factor of f, l, and n. Okay, so they solve the Poisson equation in Fourier domain. Yeah, okay, this is one thing. So people use stressed meshes when there is a solid boundary, like for in a channel flow. Uh, your velocity gradients are higher near the wall and lower in the center. So this is a rough diagram I've made. So since the gradients are very high near the wall, you need to have higher resolution here, as opposed to coarser resolution in the at the center of the wall. So what the code does is it uses a stretched mesh. That is, you can have these coarse resolutions, but the mesh stretches itself away from the wall. And the way it incorporates is you take a uniform grid. Okay, so S here is the so S is the computational coordinate and Y is the physical coordinate. So Y has to be stretched in, Y has to be non-uniform. It has to be fine near the wall. It goes away from the wall. But S can be, it can be uniform. But there has to be some transformation applied. And again, your gradients in Y has to be, expressed in terms of S. So what we do is, once this transformation is known, we solve the flow and the uniform coordinate, computational coordinate, that is with S, and then we get the derivatives and second derivatives in S, and use these expressions to get the first and second derivatives using the physical coordinate. Okay. Uh, so when you need this, the finer resolutions near a solid surface, you can use these uniform coordinates with some transformation, solve in the uniform coordinate system, and then get the solutions in the transform coordinate as well. So this is used for channel flows and boundary layer flows. Okay. Uh, so you, so they have also derived an expression for H. What is H? So H is the functional relationship between Y and S. Okay, so H here has an input of S along with other inputs of alpha, beta. These are the parameters that control the transformation. And with this, you can get Y as a function of S, where Y has a specified resolution. With some simplifications, you can get a simplified expression for H here. Anyways, these have been already implemented in the code, so you do not have to worry about these as of now, unless you need something very specific. Okay. So yeah. Okay. So mm, so any questions till now? Because I think this was enough description from my end. I mean, you must have questions at the moment, right? Hello.
I think I have to go through this again to ask any question. Most of it is going over my head. So
Okay. Sorry for that.
No, I'll once
No,
I'll go through it again. Maybe I'll get better grasp.
but you're getting the flow of it, right? Like what is
Yeah, yeah.
happening. You're not totally you're unaware of what is going on.
Yes.
Yeah. Okay. Okay. How about you, Arun? Okay. So they have demonstrated a few cases here. Okay. So they have demonstrated a Taylor Green vortex simulation, big graph flow, steady flow around a cylinder. It has a transitional channel flow and a turbulent channel flow as well. Okay. So you can go through this paper. I'll send it to you. So for this course, what I'll do is after this, I'll show you how to use Incompact 3D to run these simulations. So I'll definitely be showing you one simulation on channel flow and one on turbulent boundary layer. If you have, I mean, there are other examples on. Okay, I'll see what are the kind of flows I can demonstrate. I mean, very specific applications, I might not be able to do it right away, but I can show you um, how the Incompact 3D code is structured and how to use it. Okay. I guess this was all I had for the day. I can have a brief description on what LES is, and then we can stop for the day. What do you think?
It's fine. We can discuss Elias.
Okay, so so we have now large eddy simulations. Okay, so in DNS we were solving for the instantaneous velocity field u xt. In LES, what we'll do is we'll solve for the filtered velocity field, velocity field filtered at scale r. So let's call it UF. Let me follow the notations from the textbook. Okay. So the book uses over bar to signify the filtering operation, to represent the filtering operation. Okay. So filtering involves a convolution of u at x with a filtering kernel or over the domain. Okay. So you can understand this as follows. So let's say you have a domain here. So at some point x, so this is x. Your G might have some functional form. Let's consider it Gaussian filter for now. So it will have the form like this. Okay, and your U is a function of x, of course. So when you multiply the function at this point, Okay, so this is x minus r. So at when r is 0, this is gx. Okay, what I'm trying to say is this integral is with respect to r, which is centered at x. So your r is, going, r as an origin here at x. So your Gaussian function is also centered at this point. Okay, so when you take a product of u with g at x, what it will do is, let's say your filter function is defined such that at x equal to r, the value is 1. So at this point there is no modulation, but away from this, as the as as we move away from x, the fluctuations farther from this point are, the diminished. So these fluctuations are high, but away from them, away from x equal to r, it's diminished. Now if you take an integral of this curve with r, what you'll get is an average of u for all these fluctuations. Okay, so what this basically does is, at this point it replaces the velocity at this point with an average velocity, average velocity which depends on this filter kernel. Okay, so uh, so what basically happens is, you have your velocity signal and you apply this filter. It will keep, for all x, it will go on averaging the flow, and you'll get a filtered velocity field. Okay, now this averaging width window, this depends on the scale of filter used. So this depends on L. So okay, this Gaussian filter will have a scale L associated with it. So this will be L, not R. Okay, so what we do is, we solve for this filtered velocity field in larger dissimulations, and these high frequency fluctuations are what is modeled. So what you have now is, your instantaneous velocity field can be decomposed as the filtered and the residual. The residual is what is left. So you can call it y prime xt. So this is similar to Reynolds decomposition here. Okay. Again, you can derive, filtered velocity derivatives, convective terms, and other terms from this filtered velocity field itself. So when you write the mean equation for when you write the equation for this average velocity, you'll get something like this: by del t uj del ui by del xj plus um, let's call this tau for now. When p is filtered, okay, so analogous to the Reynolds stresses that we had seen in Rand's decomposition, this is called, residual stresses. Okay, this has contributions from the unresolved fluctuations. So all the fluctuations that were filtered out, it has contributions from those. So we are solving for ui, and we use a model for this term here, tau ij. Okay, so how is this done? Okay, Okay, just a minute. Okay, so this residual stress has this form. Okay, now there are several ways to decompose this residual stresses. There is one where you decompose it in terms of isotropic and anisotropic parts. So you have tau ij from an isotropic part, and then you have the isotropic contribution k tau, where your k tau is the residual kinetic energy. So k tau is 5 tau ii. So tau ii again is the repeated index. So you add tau 11 plus tau 22 plus tau 33 to get this thing. And this expression, the quantity, this quantity is called the residual kinetic energy. That is the kinetic energy of the filtered out fluctuations. So you can decompose tau ij in terms of the anisotropic and isotropic part, or else you can also uh, you know if you follow there is a decomposition suggested by Germano, who gives tau ij as a sum of three components: Lij, Cij, and so this is called the Leonard stress. Cij is called the cross stress, and Rij is called the subgrid scale Reynolds stress. Now this decomposition is Galilean invariant. That is, it does not change form as when you change your frame of reference. Okay, so it is usually these terms which are modeled. So the subgrid scale Reynolds stresses are often modeled. One very popular model used is the Smagorinsky model. So what the Smagorinsky model does is it models the anisotropic part of tau ij as 2 times nu r Sij. Where in analogy to your the Prandtl's mixing length hypothesis, you have your Smagorinsky length scale where nu r is Smagorinsky length scale square and the average uh, shear in the flow. So using this, they can model the the residual stresses that are there in the flow. Okay, there are other several other methods to model this thing. I'll get into the details of it maybe tomorrow. I have not prepared for this today, so this was not very good, I guess. Okay, so let's stop today. We'll continue this tomorrow. Hello. Hello.
Yeah.
Yeah, you said anything?
No, I said okay, okay. Actually, just I want to ask you something.
Yeah.
That, whatever the models just we are considering in LES or that just like Wales model in LES, you know,
Hmm.
everything they put some hypothesis into the main equations, main three equations, you know.
Huh.
So uh, when other body forces, na, just like there will be a gravity body force.
Yes.
So consider there is another body force that is being included other than gravity, then how these things will be used? Just like you said, body force, we merge it in the other components. We merge it.
Hmm.
In some cases, now we merge body force.
Yeah,
If
yeah,
this
do
is
that.
simple gravity force, we can merge it in the pressure.
Uh-huh.
But if there is a certain other forces, then what we can do, just like if there is a relation between fluid structure analysis is going on now.
Uh-huh.
This considering example where the fluid and structure both are interrelated. Yeah. Just
Okay,
like
okay.
we can think in a flexible string, na? A flow
Oh,
over a flexible string. So
so I
in
mean,
these things, multiple forces are in play.
yeah, yeah. I mean, in that
So
case,
how these things are converted?
see, if you have a structure there, let's say a fluctuating ribbon is there.
Yeah,
So in that case, the forces that are being exerted by the ribbon on the flow will not be a body force because it is only acting on the surface of that ribbon.
yeah, yeah, yeah.
Yeah. So,
I am
I
just
mean,
giving an example. If
but
there are any
yeah,
other forces, na?
yeah, there could be magneto-hydrodynamic forces, but I think in those cases you cannot include those terms in pressure, and you'll have to consider their effect as well. You'll have to solve for those. So there is, I don't think there is a way around for that. So let's say at small scales we have surface tension forces there. I don't think
Yeah.
we do not include those in pressure.
No, no, we do not
So
think about surface tension
yeah,
forces.
so we
Definitely,
if we have an additional pressure, we have to consider that. Like you seen in that equation from that paper by Lizet on in compact 3D, there was a forcing term there, right?
mm,
So likewise, we can have another forcing term for any other kind of body forces that are there in the flow. So the forcing term that they had shown, it was user dependent. They were using forcing when they wanted to enforce some kind of flow there, and they were not using that forcing when they did not want to use it. But let's say there is some physical phenomena which says that there will be some body force in the flow, then it will be part of that equation and it has to be solved. So, so for example, you can you can consider the pressure force itself as a body force. So like we have solved for pressure, we can solve for the other body forces as well. Except that it might not be conservative. Like the viscous forces are not conservative. That's why we could not absorb that in the pressure itself.
yes, yes.
Let's say if we are in a rotating frame, then there would be a centrifugal force throughout,
This,
right?
that will be involved in breaking the shear stress shear layer.
Yeah, but
That
then
won't be in.
mm, but then again, it depends on that body force. I mean, what kind of force it is. Let's say if you do not know whether it is conservative or not, then do not absorb it in pressure. I mean, we could have again solved the entire equation by considering the gravity, but again, we can. I mean, when you're solving numerically, it won't be an issue. You can solve for it. Did that answer your question?
Yeah,
Uh,
definitely. Yeah. These are some little bit of curiosity. Actually, when solving and understanding these huge amount of mathematical equations and a set of proper steps, systematic and proper in-depth steps, na,
yeah.
it's just out of curiosity that we are digesting such a huge amount of information.
Hmm.
These certain nitpickings always come into mind that what we are gonna do in these
Well,
situations.
do not get overwhelmed by these equations. I mean, these are just for the understanding. I like,
No,
okay,
no,
you're
I
using
am not.
compact. Like you can
We are
use in
getting
compact.
overwhelmed na? Because for us, we are just I am a software user. Yeah, we consider
Okay.
it a black box. Definitely, we know the mechanism what is going in behind him, but not in that in-depth manner. That how it is converting that into that FFT so much equations. No, we don't know the physics. It's such an in-depth mathematics behind it.
Okay,
And you are
okay.
telling us that things are going behind black box like this, so
Mhm.
we are getting overwhelmed.
It's okay. I mean, I don't think. I mean, the Incompact does not use spectral solver, so I told you just because I think people should know. Um because okay, even Incompact uses a spectral solution for poison, so having some idea should is a good thing. But it is not like you have to be an expert at that. I mean, if you go and look at it a few times, it will be it will seem easy. Well, not easy. It won't seem daunting at least. And
Yeah.
uh, I don't know. For spectral solutions, there are even for spectral solutions there are open source codes. I mean, unless you want to write it yourself, I don't think it would matter. But you should one should know these equations that go behind.
Yeah.
Uh,
Thank you,
anyways,
Adit.
yeah. Thank you. Hope to see you again tomorrow. Tomorrow we'll be
Okay.
discussing this thing. I'll show you the database and the Incompact 3D, and I'll demonstrate a few cases. Okay, so maybe we can work together, like you do as you follow along as I do things, right? Because if you leave
Okay.
it for
I will try.
later, I think it will be left out, and people you won't have that. You'll have that doubt in your head. Hello.
Mm-hmm. I'm listening, Adit.
Okay, so maybe have your laptops ready. Do you use Linux, both of you?
No, no.
Okay, Harsh, even you don't use Linux.
No, no, I don't use Linux.
Okay, okay. Anyways, there's no issue. Okay, okay. So let's
Okay,
speak
bye, Adit.
tomorrow. Yeah. Bye
Okay.
bye.
See you
Thank
tomorrow.
you.